Hi friends, welcome to this channel. Here we are going to look at today's daily challenge problem. So this problem is on binary tree, right? So here we want to find the lowest common ancestor of deepest leaves. So this problem actually is rather easy to digest. So here let's look at example 1. So notice that 7 and 4 are the deepest leaves. So their lowest, ancestor is 2, right? So this is just single node, so you just return itself, and here you return 2. So actually the main point for this problem is this. So if for a node, its left and right subtree trees have the same say height, so then this node itself is the lowest common ancestor of deepest leaves, right? So if you talk deepest, you actually need to think of heights or levels, right? So here it's defined like this. So the node of a binary tree is a leaf node if and only if it has no children. And the depth of a root of the tree is 0. And if the depth of a node is d, then the depth of each of its children is d plus 1. So notice that this is a recursive definition, right? So here's the definition of the lowest common ancestor of a set of nodes. It's the node A with the largest depth such that every node in S is in the subtree with root A, right? So this is some rigorous definition, but if you have practiced a lot on leetcode problem, or you have a solid background in data structures, this should be very familiar to you, right? So here, actually the problem size is also not very large, because the number node is in this bound, right? This determines the problem size. So here actually it also says that the values of the nodes in the tree are unique. So in our first version of solutions, I'm going to use this constraint or additional assumption explicitly. So this is for us to digest the details. Then in the second version of code, I'm going to write a compact one. So with that said, let's do the job. So here in the first version, if we know that for each node, because their values are distinct, so we can actually consider each value. So if we know the levels or heights of the left and right subtree, and then we immediately know which node we should return. For example, here if you look at 3, so the left subtree have a height 3, and the right subtree have a height 2. So this must not be the answer. So we move to the deeper, the subtree with the larger height. So we move here. If we look at the tree at 5, its left subtree has height 1, and the right subtree have height 2. So we still move to the higher tree, right? So we move to this node 2. Then its left subtree and the right subtree have the same height. So we return this node. So this is basically the logic. So with that said, let me write some code for you to digest, right? So here I'm going to initialize a dictionary, that's D. And then I'm going to write a function, let's call it depth, right? So what I want to do is to, given a root or just a node, so I want to, for each of the nodes, so I'm going to get the tree height or corresponding to that node. So here, if not root, I'm going to return 0. Otherwise, we do a recursive call, right? So it's depth root left and depth root right. So notice that this line of code is valid because we have checked the case if not root. For example, it's possible, right? This one or this one is null. So it's corresponding to 0 because of this if condition or if check. So now what we do? So then the root value. So it should be the 1 plus the larger of L and R, right? And then also we return this 1 plus max L and R, right? So then if you call this function, right, root, so you are going to update this D. So we can print out this D. For example, this one, for 3, so what do you get? You get a 4. So this is the height, right? So actually it's 1 larger than the level. So this is level 0, this is level 1, this is level 2, this is level 3. But for height, this has height 1, height 2, height 3, height 4. But you can shift by 1 if you like. It does not matter, or it does not change the nature of the problem. So now we have this, right? So next, what we do? So I want to do a breadth first traversal, so that the first node I found whose left subtree and the right subtree have the same height is the node we're going to return. So here I'm going to call this collections deck. So I'm going to have a root, and then basically this while loop, while q. So we get the current node as q pop left, right? And then first we want to check if not node left and not node right. It means that we have arrived at the leaf node. Then we must return this one, because this for sure corresponding also to the deepest leaves, right? So this is the case. Another case, let's just write it now. This is more logically clear. So if not, because the else part is either left or right, right? If not node left, so it means we have right, right? So we're going to do q append node right. Otherwise, so now we have left, but if we do not have not node right, then we're going to go into the left side, right? Otherwise, so we have both left and right. So then we can check the node value. So if node left value equals the node right value. So this corresponding to the height. If the height are the same, then this node is the node we are going to return. So we just return node. Otherwise, so we compare which one is larger. We move to the higher, the subtree with larger height. So if this is the case, so we're going to do q append node left, right? Otherwise, so we return q append node right. So this is actually what we did when we look at the two here. This is the return. This just translate that into the coding format. Actually, we can stop here because we know there must be some returns. So then let's do a test first. So let me. Yeah, it passes the 3 test cases. So now let's look at the generic case. Yeah, it passes all the cases. So now we understand the detail, right? So we know that binary tree is a recursive data structure. So we can actually do this part and this part in one go, right? So now let's see how we do it. So I'm going to copy this part. And then I'm going to change this one to be version v1. And then what we do is this. So we just follow the same idea, but write a more compact code. So here I'm going to define a depth first based traversal. So given the node, so I'm going to return 2 pieces of information. One is depth, or one is depth and or height, and also the corresponding lowest common ancestor, right? So if not node, so what we are going to return, so the height will be 0, and then we return null. So here, notice that what we want to return is the I want to use height. It's because just my own convention. So this is the one. And then similarly, we can do the left height and the left LCA. Let's see, as DFS node left. So this is always right, always legitimate, because we have done this if check. So similarly, we should get the right part information, right? Lowest common ancestor, DFS node right. And then basically we want to compare L and R. If they are the same, we just need to return the node, right? In principle. And if L is larger, so we go to L. If R is larger, we go to the right subtree. So now let's see. If L equals R, right? So what we want to return is say 1 plus L. This is depth. And then we have the node. This is what we want to return. Let me add some parentheses to indicate that we are returning a tuple. So otherwise, if they are not the same, so what we want to do, else, let me write like this. If L is greater than R, so what we want to do is to return, say, L plus 1, and then the left subtree and lowest common ancestor, right? And otherwise, so we're going to return R plus 1 and the right lowest common ancestor. So this will be the full code. Actually, it's the same as the first solution. However, in the return, so we actually return 2 pieces of information. So here I have changed this one to be version v1. Now let's test this solution. Let's see, what's the problem? If not node, so we're going to return 0, none. So we have so we haven't called this function yet. So here we need to call DFS root, right? So then the second one is LCA. Now let's run it. Yeah, it passes the 3 test cases. Now let's look at the generic case. Yeah, it passes all the cases. I guess with this done, that's basically about it for the coding part. So now let me make 2 remarks. First, when you do problems related to binary tree or inner tree, you can think of recursion, because those data structures can be defined recursively. This is the one. Another one is that we have a playlist related to binary tree in our channel. You're welcome to check out those videos and practice the corresponding problems. With that said, that's it for the current video. Thank you for watching.